Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In the last week, we discussed about the several, different types of instabilities. Okay, we showed that, there can be instabilities due to the interface of two fluids. Okay, and we talked about Rayleigh-Taylor instability. We talked about Kelvin-Helmholtz instability. We also showed that there can be also a wave mode which corresponds to the stability criterion, the stability, and that was the surface gravity wave. Okay, we also showed that due to the interplay of gravitational self-gravitating force and the hydrostatic pressure, there is also another possible instability which is very much possible in the star forming clouds, that is the famous Jeans instability. Okay, but we started with another instability which was which we said that it is very useful for our domestic life as well as for astrophysical context. That was the Rayleigh-Bénard convection, right? So we actually started the discussion with convective instabilities, and then we talked about this Jeans instability, and then we talked about finally the two fluid interface instabilities. Now if you remember, for analytical convenience, our models were very much simplified. So in case of real fluids and real astrophysical contexts, the subject is very difficult, and sometimes this is not even evident to solve them analytically. Then we have to take the numerical support. Okay, so we have to do simulations. Okay, so that is something a very interesting and useful piece of information for you, because very soon some of you may start your research. Okay, now in today's discussion we will discuss another aspect which is also related to the stability or instability part, that is called the oscillation of the stars. Okay, so actually it was observed. So to be very honest, the emergence of the subject astrophysics is much more recent, but the subject astronomy was very old and very ancient. Actually, people used to see stars and they got enthralled, and that's why they tried to make the observation process schematized and systematic. Okay, and that made the field of astronomy much more interesting and much more systematic as well, organized. Okay, and then of course came the intervention of geometry, trigonometry, calculus, all these mathematical things. Okay, and then of course with the increase of complexity, they started to use topological techniques sometimes for very complicated things. Okay, other geometric, well, this is also geometry, of course, other complicated geometric considerations, relativistic considerations, and also then the physical aspect came and astrophysics was born. Okay, so but the physics of the stellar oscillation is a very interesting subject that is beyond the scope of the current course. So if you are interested, you can go through the book of Kiepenhahn and Wiegert. Okay, that's a classical book on this. And there is another book which I will tell, like maybe in the live session, if someone asks me that, but of also during the lecture I will mention about that. So this is also another book specialized for oscillations of the stars. Okay, so let us start the discussion by saying that rather than the physical aspect, even astronomically, the oscillating stars were very much interesting. Okay, that's because of the simple fact that I mean, people used to observe in the sky the luminosity of certain stars. They were actually changing with time. Okay, and not changing in an arbitrary way, but periodically. And then they thought about the whole story of this oscillation. So now, I mean, before going to the equations and some analytical part or something treating mathematically, let us first have a look at the history of detection and the formulation of the stars with variable luminosity. Okay, so this is the following points will cover some of the elements of the history of the detection of stars. Okay. Now, first, for the first time, the variability of such a star was observed by Edward Pigot, okay, in the year 1784, and that was in the star Eta and in the multiple star system Aquila. So the star's name is Eta, so it is like this Eta. Okay, so Greek letter Eta. Okay, so the I mean the member stars of the Aquila multiple star system, okay, is named by Greek letters like alpha, beta, delta, and most of the multiple systems are actually named like that. And Pigot observed a variability in the star, which was the Eta of that family. Okay. Then 1786 actually, the famous star Delta Cephei, that was discovered by John Goodricke, where he also found the variability in the luminosity of the star. Now this Cephei belongs to the famous class of the Cepheid stars. So whenever we talk about the stellar oscillation, we talk about the Cepheid variables. So Cepheid variables are a class of stars, okay, whose luminosity changes periodically with time. Okay, so just a minute, yeah. That was the story for old part of the detection, this too, but the formal detection was done, and she is called the pioneer of detecting this Cepheid variables actually. That was done by Henrietta Leavitt in the year 1907. Okay, and when she detected, she actually came up with a relation between the time period and the luminosity of the stars for the Magellanic clouds. That she did in the year 1907. Okay. Now finally, maybe all of you have heard of the famous astronomer Eddington. So Eddington in the year 1917, Eddington was an engineer actually. So he is famous for verifying Einstein's theory, right? Maybe you have heard of this famous story. Okay, so Eddington actually proposed for the first time the mechanism, a plausible mechanism of the pulsating stars, that means the oscillating stars, on the basis of the heat engines. Now till now I was saying the stars are pulsating or something. Now how should it look like really? For that I will come to a picture in a minute. Okay, so basically if you just think very schematically, let's say a star is like that, and after some days you can see like this, and again after some days you will see like this, again after some days you will see like this. So this is roughly the idea. Okay, so of course this was all about the history. Now coming back to the theory part, now let us make, so Eddington gave something like in using the concept of heat engine. So that was of course the first mechanism, okay, first proposed mechanism for this oscillating stars. But nowadays we know that there are several mechanisms possible for such pulsation. One is known as kappa mechanism, one is known as the convection mechanism, one is known as the tidal excitation mechanism. All these things are there. You can search over all these things. Okay, so this is not really our current, the interest of our current course, but here we will just see that in this situation, when a star is oscillating, can we have some indication of its stability? Okay, can we have that? Or what should be the fluid property of that star, so that if a weak perturbation is made to the star's equilibrium configuration or some initial steady configuration, then should it be, when it should be unstable, when it should be stable. Okay. So first let us start the theoretical part by considering that oscillations in stars of finite size and shape must be an oscillation with not arbitrary frequency but only with certain discrete frequency. Because here I have put a constraint on the size and the shape of the star. And here you can easily understand that this will be actually equivalent to the case of a standing wave. Okay, so for example, if you have a string which is the string is actually tied to two iron rods which are rigidly fixed at the ground, and then you just put a small oscillation or create a small perturbation in the string will not vibrate with any frequency possible. It will have certain characteristic frequencies, right? So the string will actually oscillate with certain frequencies which are known as the the eigenfrequency, okay, of the whole problem. Okay, so that is exactly the same thing over here. Another thing you can see, so here nothing is actually bound or nothing is actually confined, but for example, let's say if you have a spherical with finite size if you have a spherical membrane and you put some very weak perturbation on this. Maybe some of you have heard of the famous Indian instrument tabla, and this is a percussion instrument. So if you just put some weak perturbation on this surface of tabla, then how should it propagate? Actually, it also cannot propagate with any arbitrary frequency. It propagates with some very certain, with certain frequencies, determined by the problem and its boundary values. Okay, boundary conditions, because the system is finite. Okay, so here this is the same type of case, and here actually you can see that it is very reasonable to assume that just like standing waves, what I just said, the oscillation of the stars is also expected to take place with certain discrete frequencies only. Now astronomical observations actually led us believe that most of the stars, that means for example the Cepheid variables, they are oscillating radially. Although in reality we know, and actually we will discuss a bit about that, we know the stars also suffer non-radial oscillations as well, but most of the Cepheid variable stars are oscillating predominantly radially. Okay. That means that the stars, even if it is pulsating, so if you, let's say if you are as a fixed distance r, so from the center, okay, here, so or here, or here, or here, so basically you will see the identical perturbation. Okay, so if your r is fixed, then the perturbation is fixed, of course, for a given time. Okay, so there is no theta and phi dependence. So that is the observational conclusion or observational information. So that's why just following the same piece of information, we can actually say that a weak radial perturbation for this type of stellar oscillation can therefore be modeled to be composed of a superposition, composed of terms. So you can say that this total perturbation will be a superposition of terms like this. So there will be a summation over n, Rn, which is the amplitude of the perturbation, which will be a function of r only, small r only. That means the radial distance from the center of the star, okay, times e to the power minus I omega n t. So we are again giving as a trial solution the plane wave type of solution. And you know that this is nothing but the decomposing the whole problem in terms of its eigenfrequencies. So once again, you have to remember that the system just oscillates with certain discrete frequencies, and those frequencies called the eigenfrequencies. Okay. And the amplitude of the eigenmode is given by this. Okay. Sometimes they are also called normal mode and normal frequency as well. So that means any couple. So all the normal modes are actually uncoupled. So any arbitrary perturbation which can be a coupled, which can have some coupled oscillation as well. But if you somehow can write them in terms of normal frequency and normal modes, then actually you finally will be succeeding to represent it as a sum of a number of uncoupled oscillations. Okay, that's the thing. So once again, this is nothing but practically this is equivalent to saying that any periodic function can be written as a infinite sum of sines and cosines in Fourier series, for example, this type of thing. Okay, this is analogical. Now this is true that for an arbitrary star, finding Rn, capital Rn and omega n, these are not really evident because there is no there is no concrete prescription for that. But somehow the life becomes simpler if one assumes P is equal to K rho to the power gamma. So a polytropic relationship. Gamma need not be equal to Cp by Cv. So gamma is a polytropic index, but we have this type of relation. Previously we also saw that polytropic relations are very, very useful for having some very interesting and simple analytical relations between several quantities. Okay, and also this uses as a useful acts as a useful closure, so that you don't need in your treatment the energy equation explicitly. That's a very important advantage. Okay, so if we do that, then actually we just have to talk about the stability problem or the dynamics problem until the momentum equation. So of course you understand that if we start from an initial hydrostatic state, which is of course a steady state as well. So here we start from some hydrostatic state where V is equal to 0. The weak perturbations actually can lead to instability. Okay, if omega n has a positive imaginary part. Why? That is easy to understand. So the time dependent part is given like this, e to the power minus I omega n t. So if omega n now has is like a plus ib and b is positive, then this I and this I will give you -1, and -1 gives you +1. So finally it will give a growing nature of the perturbation in time. Okay, so and that's exactly the reason for which we can say that for instability the omega n should have a positive imaginary part. Okay, now coming to one point, that if we start from the initial state, initial hydrostatic state where V is equal to 0, then we actually don't know that whether we don't know that whether the system will behave will behave in terms of, or will respond in terms of some linear wave mode, or it will lead to some instability. So we also know that the routine process for that is the linearization and then deriving the dispersion relation. But here, should we do it now? Okay, we will see. So before that, we just let me just mention that in this problem, again for simplicity, and this is very much reasonable actually for astrophysical context, that we neglect the fluid viscosity with respect to the gravitational force and the pressure gradient force. Okay, so that's exactly what I was just saying 1 second ago, that here in our case we will not perform a formal stability analysis and we will not derive a dispersion relation here, although you can start from this equation and you can actually check how should the wave modes or the dispersion relation actually should look like. Okay, so this is the nice homework, so I request you to try at home. Okay, so but for our current course, what we will do is much more simpler, and we will not even do the normal perturbation technique. I mean, we will not even use the normal perturbation techniques. We will now study something which was historically studied for the first time in order to understand the criterion stability for stability criterion for the oscillating stars, and that is the study of the motion of a fluid element in the star. Okay, so of course for that let us consider the motion of a fluid element which is subject to perturbation. So now we should not write the Euler equation or in terms of the Euler fields like that, but rather we have to think in terms of the Lagrangian derivative. So we will not use the, in the left hand side the Eulerian derivatives, but the Lagrangian derivative. It's okay. Thank you very much.